Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here begins the essay. In the year 1922, Aage Bohr, son of Niels Bohr, penned The Structure of the Atom, a treatise reflecting the burgeoning understanding of atomic architecture within the framework of the elder Bohr's own revolutionary model. This essay undertakes a section-by-section examination of the work, dissecting the claims advanced, assessing the supporting evidence, and contextualizing the arguments in light of the then current and rapidly evolving scientific landscape. Section 1, Introduction to Atomic Theory. Bohr initiates his discourse with a brief overview of prevailing atomic theories preceding his father's model. He articulates the limitations of classical physics in explaining observed atomic phenomena, specifically the perplexing stability of atoms and the discrete nature of atomic spectra. The claim is made that Rutherford's model, while accurately depicting a nuclear atom, was inherently unstable according to classical electrodynamics, as an orbiting electron would perpetually radiate energy, spiraling into the nucleus. This assertion is fundamentally sound, rooted in the well-established principles of classical electromagnetism. The work then presents the quantum postulates put forth by his father as a necessary departure from classical mechanics to account for atomic stability and spectral emission. This necessity, at the time, was a grudging acceptance, as the quantum postulates lacked a fundamental theoretical justification, serving more as ad hoc prescriptions to reconcile theory with experiment. The introduction, therefore, aptly highlights the inadequacies of prior models and sets the stage for the presentation of Bohr's model as a solution, albeit one built on somewhat shaky theoretical ground. Section 2, Bohr's postulates and energy levels. This section delineates the core tenets of Bohr's atomic model. The primary axiom states that electrons occupy only specific quantized energy levels, orbiting the nucleus in designated stationary orbits, without radiating energy. A second postulate asserts that electrons can transition between these energy levels, emitting or absorbing photons with energies precisely matching the energy difference between the initial and final states, adhering to the equation energy equals Planck's constant times frequency. The claim regarding quantized energy levels represents a radical departure from classical physics, where energy is considered a continuous variable. The assertion that electrons do not radiate while in stationary orbits directly contradicts classical electromagnetism, a point Bohr acknowledges though does not thoroughly explain. Furthermore, the relationship between energy levels and emitted photons, a cornerstone of spectroscopic analysis, is presented as a direct consequence of these postulates. The validity of this framework rests significantly on its ability to accurately predict observed spectral lines, a feat the work proceeds to demonstrate. However, the fundamental origin of these discrete energy levels remains unexplained within the postulates themselves, representing a significant, acknowledged limitation. Section 3. The hydrogen atom and spectral series. Bohr applies his model specifically to the hydrogen atom, employing the quantized energy levels to derive a mathematical formula for the wavelengths of emitted light. The calculation proceeds by quantizing the angular momentum of the electron, setting it equal to integer multiples of Planck's constant divided by 2 pi, often referred to as h bar, which is introduced here, though not by name or abbreviation. He employs this quantization condition alongside classical electrostatics to determine the allowed radii of the electron orbits and, consequently, the corresponding energy levels. This results in the well-known Rydberg formula for the wavelengths of the hydrogen spectral series. 1 over wavelength equals the Rydberg constant multiplied by 1 over the square of a first integer minus 1 over the square of a second, larger integer. The derived formula exhibits remarkable agreement with experimentally observed hydrogen spectra, including the Balmer, Lyman, and Paschen series. The success of the model in predicting these spectral lines lends significant support to the validity of its underlying postulates. However, the derivation relies on a mixture of classical and quantum mechanics, a hybrid approach that lacks full theoretical consistency. The quantization of angular momentum is, at this stage, an assumption rather than a derivation from a more fundamental principle. Section 4 Correspondence Principle and Limitations of the Model. Recognizing the inherent limitations of his model, Bohr introduces the correspondence principle. This principle proposes that, in the limit of large quantum numbers, quantum mechanics should converge with classical mechanics. He argues that the frequency of radiation emitted during a transition between adjacent energy levels with high quantum numbers should approach the classical orbital frequency of the electron. This correspondence is presented as a bridge between the seemingly disparate worlds of quantum and classical physics. The claim that classical physics emerges as a limiting case of quantum mechanics offers a conceptual justification for retaining certain classical notions while simultaneously embracing quantum postulates. However, the correspondence principle is more of a heuristic guide than a rigorous derivation. It provides a means of justifying the applicability of classical concepts in certain regimes, but it does not provide a fundamental explanation for the transition between quantum and classical behavior. The work acknowledges that the model fails to accurately predict the spectra of atoms more complex than hydrogen. It also identifies the inability to explain the intensity of spectral lines or the details of the Stark and Zeeman effects as further shortcomings. These limitations highlight the need for a more sophisticated theory capable of addressing the complexities of multi-electron atoms. Section 5 Atomic Number and Periodic Table. Bohr attempts to extend his model to explain the periodic table of elements. He posits that the chemical properties of an element are determined by the number and arrangement of electrons in its outermost electron shell. The claim is made that elements with similar electron configurations in their outermost shells exhibit similar chemical behavior. He proposed that the atomic number, which represents the number of protons in a nucleus, also signifies the number of electrons in a neutral atom. This connection, while experimentally verified, remains somewhat ad hoc within the context of the model. Bohr suggests plausible electron configurations for various elements, attempting to correlate these configurations with their positions in the periodic table. However, the precise arrangement of electrons in multi-electron atoms remains speculative, as the model lacks a detailed mechanism for calculating these electron configurations. The explanation of chemical periodicity remains largely qualitative, offering suggestive correlations rather than precise predictions. This section exemplifies the challenges of extending Bohr's model beyond the simplified case of the hydrogen atom. Section 6 X-ray spectra and Moseley's law. The work addresses the topic of X-ray spectra, drawing upon the experimental work of Henry Moseley. Moseley discovered a systematic relationship between the frequency of X-rays emitted by an element and its atomic number. Specifically, the square root of the frequency is proportional to the atomic number minus a constant, known as Moseley's law. Bohr argues that this relationship provides further support for the idea that the atomic number represents a fundamental property of the atom, namely, the number of protons in the nucleus and, equivalently, the number of electrons orbiting the nucleus. He suggests that X-ray emission arises from transitions involving inner shell electrons, which are less affected by the complex interactions of outer shell electrons. The agreement between Moseley's law and experimental data is presented as strong evidence for the validity of the model's central tenets. However, the explanation of Moseley's law remains somewhat phenomenological, lacking a detailed theoretical derivation from first principles. The work relies on the empirical observation of Moseley's law to bolster its claims regarding the significance of the atomic number, rather than providing a rigorous theoretical framework for its origin. Section 7 Electron Configuration and Chemical Properties. This section expands on the connection between electron configurations and chemical properties. Bohr reiterates the assertion that the arrangement of electrons in the outermost shell dictates an element's chemical behavior. He elaborates on the concept of valence electrons, those residing in the outermost shell, and their role in chemical bonding. The work suggests that elements tend to gain, lose, or share electrons in order to achieve a stable electron configuration, often resembling that of a noble gas. This tendency is presented as the driving force behind chemical reactions. The explanation of chemical bonding remains qualitative, relying on heuristic principles rather than precise calculations. The work acknowledges the complexity of interatomic interactions and the limitations of the model in providing a detailed account of chemical bond formation. The discussion of electron configuration and chemical properties serves primarily to illustrate the potential of the model to explain chemical phenomena, rather than providing a definitive theory of chemical bonding. Section 8, Isotopes and Atomic Weight. The treatise addresses the existence of isotopes, atoms of the same element possessing different atomic weights. Bohr explains that isotopes have the same number of protons but differ in the number of neutrons within their nuclei. The claim is made that isotopes exhibit nearly identical chemical properties, as their chemical behavior is determined primarily by the number of electrons, which is the same for all isotopes of a given element. The discovery of isotopes is presented as a refinement of the concept of an element, demonstrating that elements are not necessarily composed of atoms with identical atomic weights. This recognition paved the way for a more nuanced understanding of nuclear structure and the role of neutrons in atomic stability. The explanation of isotopic properties is straightforward and consistent with the established understanding of atomic structure. The work accurately portrays isotopes as variations of a given element, differing only in their nuclear composition and Section 9, Nuclear Structure and Radioactivity. Bohr delves briefly into the emerging understanding of nuclear structure and radioactivity. He acknowledges the existence of radioactive elements, which spontaneously emit particles and transform into other elements. He suggests that these radioactive processes involve changes within the nucleus, rather than the electron shells. The work presents a rudimentary picture of the nucleus as composed of protons and neutrons, although the neutron had only recently been hypothesized at the time of this writing, and was yet to be experimentally confirmed. The recognition of radioactivity as a nuclear phenomenon represents a significant shift in understanding, distinguishing it from chemical reactions, which involve changes in electron configurations. The discussion of nuclear structure and radioactivity remains limited, reflecting the nascent state of nuclear physics in the early 1920s. The work provides a brief overview of these topics, highlighting their importance for a complete understanding of atomic structure. Section 10, Conclusion and Future Directions. In the concluding section, Bohr summarizes the accomplishments and limitations of his model. He emphasizes the model's success in explaining the hydrogen spectrum and its contribution to understanding the periodic table and chemical properties, the model's reliance on quantum postulates, its inability to fully account for multi-electron atoms, and the lack of a detailed theory of nuclear structure are acknowledged as significant limitations. The work concludes with an optimistic outlook, suggesting that future research will build upon these foundations to develop a more comprehensive and accurate theory of the atom. The conclusion provides a balanced assessment of the model's strengths and weaknesses. It acknowledges the significant progress made while recognizing the remaining challenges. The hopeful tone reflects the excitement and anticipation surrounding the rapidly evolving field of atomic physics in the early 20th century. The strength of Aage Bohr's 1922 presentation resides in its clear articulation of the Bohr model's postulates and its ability to explain, even if only qualitatively in some instances, a wide range of atomic phenomena. The explanation of the hydrogen spectrum, the connection to Moseley's law, and the attempt to rationalize the periodic table all contribute to the work's significance. However, the model's inherently ad hoc nature, its reliance on a mixture of classical and quantum mechanics, and its inability To fully address the complexities of multi-electron atoms represent significant drawbacks. The correspondence principle, while conceptually useful, remains a heuristic guide rather than a rigorous derivation. The work's limitations ultimately paved the way for the development of more sophisticated quantum, mechanical theories that superseded the Bohr model, providing a more complete and accurate description of atomic structure, representing a fundamental shift in our understanding of the microcosm.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.